This video answers two questions related to dynamic programming. When is it useful, and how do you apply it? To better understand dynamic programming, let's review recursion and memoization. Recursion is a top-down approach for problem solving. Solutions are found by breaking larger problems into smaller subproblems. One or more base cases limit recursion depth, and a solution is given once the stack completely unwinds. Recursive algorithms can be elegant in their simplicity, but they can also be exponentially inefficient. Consider the Fibonacci sequence. It's a simple pattern where each number in the sequence is the sum of the previous two numbers. Starting from 0, the pattern looks like this. To find the nth Fibonacci number recursively, break the problem into two smaller subproblems n-1 and n-2, and continue until the base case is hit. Try to spot the repetition occurring in the solution. The recurrence looks like this. As an aside, there also happens to be an interesting pattern developing in the count totals. If we choose a larger n like 40, it becomes obvious that the repetition is increasing exponentially. In this case, we've resolved Fibonacci 2 nearly 64 million times, and we should only need to solve it once. Worse, we've created a recursive call stack large enough to overflow a 32-bit memory space, and we've also wasted considerable time reaching that point. In other words, it's not a very efficient algorithm. We can drastically improve the recursive algorithm by removing the repeating subproblems. One way to do this is called memoization. Memoization involves using memory to record past solutions. Before solving a subproblem, we do a memory lookup and determine if we already know the solution. When a solution is already known, the value is simply retrieved and no time is wasted duplicating that effort. Memoization provides a drastic improvement over our original top-down solution. In terms of runtime complexity, we've effectively improved the original n-squared algorithm and upgraded it to a linear one. Dynamic programming is essentially memoization in reverse. Solutions are derived from the bottom up instead of from the top down. Finding the nth Fibonacci number with dynamic programming is straightforward, and you've already seen it at the start of this video. As a reminder, here's how we defined the Fibonacci sequence. With this formula, we simply find the nth number in the sequence starting from the base case. Notice how easy it is to find the 40th Fibonacci number. Like memoization, this solution is also linear in n. Dynamic programming can be used to solve problems with these two properties, optimal substructure and overlapping subproblems. A problem that can be solved by breaking it into smaller, easier to solve subproblems has optimal substructure. For example, each Fibonacci number in the sequence was the sum of the two previous numbers. The pattern between steps is always the same. When a solution involves solving the same subproblems multiple times, it has overlapping subproblems. For example, the subproblems in the Fibonacci sequence have an exponential amount of repetition. In other words, subproblems shared the same partial solutions. Fibonacci is a good candidate for dynamic programming because it has optimal substructure and overlapping subproblems. Let's practice by solving the Fibonacci sequence formally. First, we state the problem. Find the nth Fibonacci number. Dynamic programming builds a solution incrementally by storing solutions to successive subproblems in a table. We need to define what these values represent. When defining a solution, let's use T for table, N and M for sizes, I, J, and K for looping, and A, B, and C for any datasets. With that, we can define a value in the table as follows. T of I represents the ith number of the Fibonacci sequence. Next, let's define the recurrence. The recurrence explains how T of I is derived. A recurrence can include equations, loops, base cases, limits, and conditions. In the case of Fibonacci, we state the two base cases and how any individual value in that table can be derived. Next, we use pseudocode to describe how to use that recurrence to find a solution. Next, we need to analyze the algorithm's asymptotic complexity. In this case, we have a couple of constant time assignments and a one-dimensional loop, so our time complexity is linear in terms of n. We write this using big O notation as O of n. Now that we understand some of the fundamentals, let's apply dynamic programming to a harder problem. Given an unlimited amount of $2 bills and $5 bills, determine if exact change can be made. Is dynamic programming a good solution for this problem? It might help to begin thinking about the problem using a top-down approach. Let's try to make change for a $9 bill using a stack of $2 and $5 bills. Starting at $9, we create two branches. One branch subtracts the $2 bill and the other subtracts the $5 bill. We end up with three equivalent solutions: a $5 bill and two $2 bills, a $2 bill, a $5 bill, and a $2 bill, or two $2 bills and a $5 bill. These solutions are just permutations of the same set of bills. So is the problem a candidate for dynamic programming? Well, we can solve the problem by dividing it into smaller subproblems, so it has optimal substructure. And the subproblems reoccurred across its subtrees, so it has overlapping subproblems as well. Depending on the complexity of the problem, you may need some time to think about your approach. Feel free to pause the video and think about how you might solve the problem before continuing on to the solution. By using a bottom-up approach, we're building new solutions based on smaller problems we've already solved. One approach to our current problem is to treat the table index as the dollar amount that we need to make change for. If we can make change for I dollars, set the value at T of I to true, otherwise set it to false. As we iterate over I, we can continue building on top of past solutions until we hit the answer we're looking for at n. Using this approach, we can define a value in our table as T of I is true when exact change can be made for I dollars and false otherwise. For example, if we only had $2 bills and every T that's even would be true and every T that's odd would be false. Before defining the recurrence, let's define a few terms. N is the value to make change for. A is the set of denominations, either a $2 bill or a $5 bill in this case. And M is the number of denominations, or the size of the set A. Our base case is T of 0, and we set it to true because you can always make change for nothing. For every other cell in the table, we check each denomination that we have. In our case, A has a set of $2 and $5 bills. When we check to see if we can make change for the $2 bill, we look back at T of I minus 2. And when we check the $5 bill, we look back at T of I minus 5. because those are the solutions we're building upon. If the solution at that index was successful, then so is t of I. The recurrence will two loops. I iterates over the table t's index, and j iterates through the set of bills in A. The value of I is between 1 and the value to make change for at n, and the value of j is between 1 and the number of bills in the set A. Since 0 is our smallest table index, we append an additional guard to prevent accessing negative table indexes. This might look a bit complicated at first, so I encourage you to take a minute to try and work the problem out yourself. The more time spent solving these problems, the easier it gets. Now we convert the recursion into pseudocode. When I is larger than 0, we assume t of I is false by default, and true only when it can append to another successful series from a previous subproblem. We have a single constant time assignment with a nested loop. Since n and m are independent, the big O notation is written as O of n times m. Thanks for watching this tutorial, and I hope you found it useful.